Hello, this is a short video abstract about our paper on the interplay between CT and Singlet exciton emission and its impact on voltage losses in organic solar cells with small driving force. I'm Dieter Neer, I'm the last author of this publication. So what is the motivation of our work? At VUC, the value of the open circuit voltage is given by this equation containing the ratio between the total recombination current under illumination divided by the total recombination current in the dark. That, according to Rao, can be rewritten by this term, which now contains the ratio of the total recombination current under illumination divided by the radiative dark recombination current plus a term with the electroluminescence efficiency. Now, if the CT energy comes closer to the energy of the local singlet excitons, people proposed that a quite significant fraction of recombination goes through the singlet state. Modern non-phonon acceptors show quite efficient exciton emission, and that led to the conclusion that this increases the electroluminescence efficiency and with that also the VOC. This is exactly what we want to address in the following. For this, we choose a special system. It's the blend of a low band gap polymer with a mixture of two fullerenes. Why we choose that polymer? Because it forms very stable aggregates, and we could show that the absorption but also the emission properties of then the lowest energy singlet state is independent of the choice of the fullerenes. On the other hand, with this mixture of these two fullerenes with different LUMO energy, we can tune the CT energy. This is nicely shown here, where in emission, the peak of the CT emission blue shifts towards the energy of the singlet exciton, and the contribution of the singlet exciton to the electroluminescence increases with increasing ICBA concentration. On the other hand, we see a very significant increase of the VOC once we have a high ICBA concentration. That would indeed suggest that the increase in VOC goes along with the appearance of a strong singlet exciton emission. We then decomposed the electroluminescence spectra and also the ELQY spectra of all of our blends. With that, we could determine how the singlet recombination and the CT recombination affects the radiative VOC, shown here, and the VOC, the actual VOC, shown here as function of the S1 CT gap. It turned out that the radiative VOC is, particular for small offsets, entirely dominated by the singlet recombination, and that is shown in that equation where in the denominator the singlet exciton properties dominate. On the other hand, the VOC, the singlet recombination would predict a very high and constant VOC, while in truth we see that the VOC increases with smaller offset but never approaches this value. From that we concluded that the VOC is determined by the non-radiative decay of the CT state, and that in this expression the CT properties dominate. This in turn means that the singlet emission properties and the efficiency of singlet emission does not at all determine the VOC. To understand this, let's turn again to the initial equation. This is the term I have shown on the first slide, which contains the electroluminescence efficiency. That is in general given by this term containing the singlet and CT radiative currents divided by all currents including the non-radiative CT and S1 recombination. In our low offset systems, we could show that the radiative term is determined by the Singlet excitons, but the non-radiative by the CT recombination. That leads to this equation. On the other hand, the external radiative efficiency of the Singlet state, so like the PL efficiency, is given by the radiative divided by the non-radiative Singlet recombination. But for all of the systems we studied, this term is smaller than this one, as also displayed here. Therefore, the Singlet emission efficiency has no influence on the ELQY, even in our low offset systems, and with that does not boost the VOC. So what in future we have to understand is what determines the non-radiative current of the CT recombination and try to reduce that as much as possible.